Hi everyone! Today let's talk about session 11.9, curvature and normal vectors. First topic, arc length as a parameter. We usually use the parameter t as the time to represent a curve. We now introduce the arc length parameter s. The length of the integral in s equals to the length of the curve generated. So this is the definition. Let gamma of t describe a smooth curve for t greater or equal to a. Then the arc length function is given by s of t equals the integral, the definite integral from a to t of the speed. Okay, speed is the length of the velocity vector. So here where the length of the velocity vector is the length of the displacement prime, okay? Equivalently, ds dt equals to the speed, okay? Greater than 0. If the speed equals 1, for all t greater or equal to a, then the parameter t corresponds to the arc length. Okay. So let me draw some picture here. So suppose we have a graph, a curve like this. At t equals 0 is here, and when t equals 1 here, and t equals 2 here. Okay, so it's going to this direction. And what happens if the speed is faster? Then maybe t equals 0 is here, t equals 1 is here, t equals 2, t equals 3, t equals 4. Okay, so at different time you can see how the particle move. And what is special about the arc length parameter? So the arc length parameter, let's say this is s of 0. Okay, and this is s of 1. The fact is this length it travels actually has the length 1. Okay, so the parameter values equals the length of the curve it generates from the point s equal to 0. So let's say here, this is s equals 5. Then the length from s equals to 0 to s equals to 5 has length, let me use a different color. So it means this part has length 5. Okay, so that is the arc length parameter. Just looking at the parameter values, we know what is the length of the curve compared to the starting point. Okay. And the relation between the t parameter and the arc length parameter is this definite integral. Okay, so let's continue to look at the following examples. Consider the ellipse gamma of t equals 2 cosine t, 2 sine t, 4t for t greater or equals 0. A. Find the arc length function s of t. B. Find another description of the ellipse that uses arc length as the parameter. Okay, so first, let's find the arc length function. Okay, so we need to find a velocity. Velocity is the displacement prime, okay? Derivative of 2 cosine. Derivative of cosine is minus sine. So we have 2 sine t. Derivative of sine is cosine, so we have 2 cosine t. Derivative of 4t is 4. Okay, then what is the length of this tangent vector of velocity? It equals to h coordinate square. So 2 square is 4, then we have sine t square. 2 square is 4, we have cosine t square. And 4 square is 16. So here, this guy, you can, 2 square is 4, so just 4, not 4 square. You can see we can fetch out the 4, then we have sine square plus cosine square. Well, that's always equals 1. So this guy is square root of 4 plus 16 is 20. And then 20 is 4 times 5. So this is 2 square roots of 5. Okay, so By definition, the at-length function equals a, let's say a is from 0 to t of our speed, which is 2 square root of 5 dt. Okay? Sorry, we should use another variable. So let's use u, okay? Alright. So this is 2 square root of 5u, a value from 0 to t. It means we plug in t first, subtract, we plug in 0. But when we plug in 0, it's just 0. So this is the at-length function. B, find another description of the ellipse uses at-length as the parameter. Well, we have the relation s equals 2 square root of 5t. Then what is t? T is s over 2 square root of 5, right? Now we can then plug in. So we can plug in t equals s over 2 root 5. Then we have 2 cosine s over 2 root 5. 2 sine of s over 2 root 5. And 4t, so 4s over 2 root 5. Well, you might cancel the 4 and 2, so that's why you only get 2s over square root of 5. So far, so good? So this is how, like, giving any parameter, we can always convert it to the at-length parameter. Okay, if we're able to integrate the speed function. But sometimes if the speed function is quite complicated, then we might not able to integrate and get a nice formula. Okay, but in general, this is a method. Okay, next topic, curvature. Imagine driving a car along a windy mountain road. The velocity is changing in two ways, speed and direction. Okay, we call that the unit tangent vector is, we have the derivative of the displacement over the length of the derivative of the displacement. So that's the velocity over the magnitude of the velocity. Because t is a unit vector, its length does not change along the curve. The only way it will change is through a change in the direction. The magnitude of the rate at which the direction of the unit tangent vector changes with respect to the at-length is the curvature of the curve. So curvature measures like how fast the direction is changing. Okay, it's not measuring the speed, it's measuring the direction. So if we have a large curvature, it means the curve turns quickly. So for example, like this. It turns quickly. Small curvature, well, the curve turns slowly. So like that, turns slowly. Okay, the curvature is k of s equals the length of the derivative of the unit tangent vector with respect to the at-length parameter. Okay, so t is the unit tangent vector and s is the at-length parameter. And then, so keep in mind, this is the definition. By chain rule, and we use the fact that ds dt equals to the speed, then we can get k, the curvature. This is actually a Greek letter, kappa. Okay, so kappa equals the length of dt ds. And it equals, because of chain rule, we can like insert dt in the denominator for both the numerator and the denominator. Okay, and then we can separate them. So the top, now you can see the top guy, we have the derivative of the unit tangent vector now with respect to time, and the bottom is the speed. Okay, that is the length of the tangent vector. Okay, So this is t prime of t over r prime of t. Okay, let's continue. So example, find the curvature of gamma of t equals 3 plus 4t, 2 minus t, and 7 plus 5t. Part B, find the curvature of the circles. 5 cosine 3t and 5 sine 3t. First, we want to compute the derivative. Well, the derivative of constant is 0, derivative of 4t is 4, derivative of the second coordinate is -1, and the last coordinates. Okay, because they're all linear functions, then the derivative is just the coefficient of t. Alright, then what is the length of it? Well, square root of 4 squared plus -1 squared plus 5 squared. This is the same as 16, 1, and 25. So the answer is 42. Now, what is the unit tangent vector? Well, unit tangent vector is the velocity over the length of the velocity. Okay, so we have 42 minus 1 over 42, 5 over square root of 42. Okay, so this is the unit tangent vector. And then we want to take the derivative of that. Well, take the derivative of that. What do we get? Well, because they're all constants, so we just get zeros. And then what is the magnitude of a zero vector? Is just 0. So what is the curvature in this case? We have the magnitude of t prime over the magnitude of gamma prime, so that's 0 over square root of 42, which is 0. So curvature is 0. Let's look at it. Why is that? Have you recognized what this is? This is actually a line. So for a line, do you change direction? No! We don't change direction. So that's why the curvature is 0. So it kind of makes sense, right? Okay, let's continue to look at part B. So we repeat the same process. Prime derivative of find cosine 3t. Derivative of cosine is minus sine, but because of chain rule, we have an extra copy of 3 multiplied by 5, 15 sine 3t. Derivative of sine is cosine, and then 3 times 5 is 15 cosine 3t. And then what is the speed? Well, that's the square root of 15 squared sine 3t squared plus 15 squared cosine 3t squared. But we see after we fetch out the 15 squared, sine squared plus cosine squared is just 1. So this is the same as square root of 15 squared, which is 15. Alright, then what is the unit tangent vector? Well, unit tangent vector is gonna be r prime over the magnitude of r prime. So when we divide it by 15, then we just have minus sine 3t cosine 3t. So far so good, everybody? Okay, and here let's see. So what is t prime? Well, then t prime is here square root of sine 3t squared plus cosine 3t squared. So that will give us 1, right? And oh, sorry. I just calculating its length. No, we're not ready. We should take the derivative. Okay, the next step we calculate the length. Derivative of the sine is cosine, so minus, but because of chain rule, we have 3 in front. Derivative of cosine is minus sine, but we have 3 in front. Okay, now here, we can take the length. The length is the square root of 3 squared cosine 3t squared, 3 squared sine 3t squared. The sine squared plus cosine squared is 1. This is just the same as square root of 3 squared, which is 3. Okay, now what is our curvature? Our curvature is t prime over gamma prime. Okay, so that is 3 over 15, and that's 1/5. So far, so good, everybody? Okay, and you can see here, the curvature of the circle is a constant. It's not a function of t. Why is that? So think about a circle, okay? When it goes around here, then the curvature is fixed because when we measure how we change the direction, and it's constant. Okay, so we can see this the speed doesn't matter. Okay, if even though we might use another parameter t or different parameter t, you can change the speed, but the shape of the circle, the trajectory of the particle is still the same. So the curvature of a circle only depends on the circle, the size of the circle, and it does not depend on the speed. Okay. And so here, only the shape matter. Okay, and in fact, do you notice that this is a circle with radius 5? Okay, so later on, we'll read it again for a circle with radius r. Then the curvature is 1 over r. Okay, so we will talk about this fact again later in this session. All right. And actually, we have other curvature formulas. Okay, so formula 2, suppose velocity is gamma prime and acceleration is gamma prime prime, then the curvature equals the length of acceleration cross velocity over the speed cube. And we have the formula 3 only works for plane functions. Okay, so if we have a plane function, okay, at y equals f of x, suppose f is twice differentiable, then the curve has the curvature. We use the second derivative and then find the absolute value of that, divided by 1 plus the first derivative square, and then that quantity to the 3/2. And this is formula 4. It only works for plane curves. Okay, so suppose we have a parametric form, right? Gamma t equals ft gt, and it's in R2, okay, plane curves. Suppose f and g are twice differentiable, then the curve has the curvature, so the numerator becomes f prime g prime prime minus f prime prime g prime. The denominator becomes f prime squared plus g prime squared to this quantity to the 3/2. Okay, so it depends on the problem, then we can pick the formula correspond to it, and then we can calculate. Okay, so now we have learned 4 formulas for curvature. The first one is, by the definition, we use the magnitude of t prime over the speed, okay? And then we learn those formula 2, 3, 4. Okay, let's continue to look at examples. A. Find the curvature of the helix using formula 2. So what is formula 2? Keep in mind here we have acceleration cross velocity, okay, and then calculate the magnitude of it divided by the speed cube. Okay, so we need to find the velocity and acceleration. So what is the velocity? Well, that is the derivative of the displacement. So derivative of a cosine t is negative a sine t. Derivative of a sine t is a cosine t. Derivative of bt is b. How about the acceleration? Well, then we take one more derivative. Derivative of sine t is cosine. So minus a cosine t. Derivative of cosine is minus sine t. Derivative of constant is 0. Okay, and next we want to calculate a cross v. So how do we calculate cross product? We have the first row I, j, k, and then we have the a in the second row. So minus a cosine t minus a sine t, 0. Then we have minus a sine t, a cosine t, b. So see, this is plus minus plus with plus I times the minor, okay, so which is the determinant of the submatrix, minus a sine t, 0, a cosine t, b. Then minus j times the minor of deleting the first row, deleting the second column. So we have negative a cosine t, negative a sine t, 0 and b. And then we have plus k times the minor, which is the determinant of the submatrix, minus a cosine t, oops, not enough space, minus a sine t, minus a sine t, a cosine t. Oops. Okay, let's continue. So we have I cross multiply. So we have minus ab sine t minus 0. And then j, we have cross multiply minus ab cosine t minus 0. Okay. And k, we have cross multiply, so negative a squared cosine square, right? But then minus negative become positive, a squared sine t squared. Okay, now what happened? So we have negative ab sine t I minus minus become plus, plus ab cosine t j. And then here, well, you can factor out negative a squared, then you have sine squared plus cosine squared. That's 1. So minus a squared k. So if we want to write into component form, we have minus ab sine t, ab cosine t, and negative a squared. Okay, so this is the cross product and it's a vector. Remember that product is a number, scalar, but cross product is a vector. Now we can compute the magnitude of it. So that is first component square, second component square, last component square, which is a to the 4th. Well, here you can see, well, you can combine this guy, and then you can factor a squared, b squared, but then sine squared plus cosine squared is 1. So that's why here we have a squared, b squared plus a to the 4th square root. And here we can factor a squared, then we have a squared plus b squared. take the square roots. Well, if a is positive, then square root of a squared is just a. Then we have square root of a squared plus b squared. Okay, next for the denominator, we want to compute the speed. Well, the speed is the square root of a squared sine squared plus a squared cosine squared plus b squared. Well, this guy is just a squared. So we have square root of a squared plus b squared. Okay, now let's see. What is the curvature? Well, that is the magnitude of the cross product, a square root of a squared plus b squared, and then the denominator is the speed. The speed to the cube. But it was square root, so this is 3/2. Oh, you know, the top we have a squared plus b squared. Square root of that is like to the 1/2. So that's why 1/2 and 3/2 they cancel. We only have one copy at the bottom. So that's why we only left with a squared plus b squared at the bottom. So far so good, everybody? Okay, so this is the curvature of a helix. Let's continue. And you can see the helix, this curvature only matter is the shape, okay, the shape of the helix. Okay, maybe I should do like this. So only the shape is matter, not the speed. Okay, not the let's see. What I mean is it's because this guy, it has no t in it. It does not depend on the parameter t. So that's why here the curvature only depends on the shape of the curve. Okay, let's continue. Part B, find the curvature of the functions f of x equals ln of x using formula 3. Okay, so let's see here. Let me use a different color. And furthermore, you can see on the helix at each point the curvature is the same. So as our previous example on the circle, the curvature at each point of the circle is the same. So that's why it's not a function of the t. Okay, is constant. The curvature is constant because of the curve, the shape of it. It has constant curvature along each point on the curve. Okay, so part B, we have f of x equals ln of x. We want to use formula 3. Okay, so we need to take the second derivative and we need to take the first derivative. Okay, so let's see here. Fx equals ln of x. Then f prime of x equals 1 over x, right? And then how about the second derivative? Well, this is the same as x to the minus 1. So the derivative of that is negative x to the negative 2. So it's negative 1 over x squared. Okay, so keep in mind that formula. We have the absolute value, not magnitude, because this is just numbers, right? So it's scalar value function. So we have the absolute value of the second derivative over 1 plus first derivative squared to the 3/2. Okay, so curvature is second derivative absolute value of that. Bottom we have 1 plus first derivative square and then to the 3/2. Okay, because of the absolute value, we get 1 over x squared. Here, we have 1 plus 1 over x squared to the 3/2. Okay, we can simplify it. This is the same as we take the common denominator, we get x squared plus 1. But this guy to the 3/2 is the same as saying we have x squared plus 1 to the 3/2. Well, then over x squared to the 3/2. This 2 and half cancel, we have x cubed. So now let's multiply the top and the bottom by x cubed. X cubed and x cubed cancel. X cubed and x squared, we have an x left on the top. And then we have x squared plus 1 to the 3/2. So far, so good, everybody. So you can see in this case, the curvature is a function of x. So why is that? Well, think about the logarithm function. So logarithm function look like this. So the curvature at each point actually changes. Okay, so and eventually it's like more flat here. So you that's why you can see is this guy is a function of x. Oops. So far, so good, everybody. Okay, let's continue. So part C, we want to find the curvature of the ellipse using formula 4. So this is a parametric equation, right? Parametrization of the ellipse. And we want to use formula 4. So f is the first coordinate function, g is the second coordinate function. So okay, we want to the top we want to have f prime, f prime prime, g prime, and g prime prime. Okay. So here let me use a different color. C. So gamma of t equals a sine t, b cosine t. Okay. So we know this is f, this is g, right? F prime equals a cosine t. F prime prime is minus a sine t. G prime is negative b sine t. G prime prime equals negative b cosine t. Alright, then our curvature. So the numerator is the absolute value of f prime. F prime is a cosine t times g prime prime. So negative b cosine t. Then minus f prime prime, which is negative a sine t times g prime. So negative b sine t. And the denominator we have f prime square plus g prime square, and then to the 3/2. Okay, let's see. What's the top? Well, the top we have ab cosine t squared, and then because this guy is minus, and this guy is also minus ab sine square, right? And the bottom stay the same. Okay, so you can see the top is the same as we can factor out minus AB, and then what's left is cosine squared plus sine squared. Well, that is 1. But absolute value of negative AB is just AB. So suppose A and B are both positive. Then we have AB over A squared cosine t squared plus b squared sine t squared to the 3/2. Okay? And you can see this is a function of t. So in this problem, we have an ellipse, right? So let's say this is the ellipse. It doesn't look nice. Let me draw a better one. Okay, so we have the ellipse. Now you can see at each point. So you can see at this point, I would say it turned more quickly than this point. Okay, so we will say here we have because it turned more quickly, we will have a larger curvature. Here it turns more like slowly, then it will have a small curvature. So the curvature change with respect to the time, because at different points the curvature is gonna be different. Okay, but you can see, because it also depends on the shape, so you can see at this point the curvature, I can see this curvature and this curvature is gonna be the same, right? And then this curvature and that curvature is gonna be the same. So that's why what I mean by is the curvature depends on the shape of the curve. Okay, so if the shape, like your circle, at different points, like the change of the direction looks like the same, then they will have the same curvature, and also like the helix, they will have the same curvature. And then you might have a curve like this ellipse. At some points, the curvatures are the same, and at some points the curvature there are different. Okay, so the shape decides the curvature. So far, so good, everybody? Okay. And that's it about the topic of curvature. Let's continue in the video part B. See you soon.